And hello again, everybody. Today we're going to go over something really unique to a gas permeable lens. In one of our last units, we talked about soft lenses, and we had a cool handout about soft lenses and how they work. And generally, the power which to get, the power of the lens is the power that the patient gets. So if you have a spherical lens of a -225, that's what it is. Normally what we try to do is we take the spherical equivalent if there's little or no astigmatism to the patient in the patient's prescription. We'll vertex that if it's over a ±4. If you tend to have more astigmatism, higher levels, say 1 diopter, maybe even 0.75 diopters or more, we have to start building that into the lens, and we actually put the astigmatism into the lens. And we use what are called soft toric lenses. Gas permeables are a whole different ballgame in that, unlike a soft lens, which sort of drape, almost if you put saran wrap, for lack of a better analogy, over a basketball, which would match the shape, it's almost like putting a bowl on the basketball. The basketball has its shape, the bowl has its shape, and it may exactly match up with the basketball. Sometimes it'll be a little bit less steep, a little flatter than the basketball surface. Sometimes it'll be a little bit more steeper than that of the basketball surface. Well, that's what a GP is like. It's like that little ceramic bowl or a glass bowl, if you will. And because it maintains its shape, tear film will actually work its way under that lens. And because there's a specific little clearance there, there's a little area there where there's a tear film there, and it can have a specific shape, it actually contributes to as almost like another refracting medium in the contact lens when you're doing GPs. So today's lecture will be about that tear lens, how it works, what it looks like, how it affects how we design a lens. And it is a little bit more complicated than a soft lens, but I will tell you, if you understand the gas perms, then the soft lenses tend to be actually easier. So that's why we do a lot more with the gas perms, because it is a different, more difficult concept. So what we're going to do today is we're going to share our screen. And we have a neat little PowerPoint here for you today, and I'll post this up on Blackboard. And so that way you can look at both the lecture here and tape it and watch it whenever you want and re-watch it whenever you want. And you'll also have access to follow along with the PowerPoint. Now, I do have to make a note. Let's actually unshare this for a moment. Hopefully you're watching this. I will tell you that I have a handful of students that they're only doing what they need to do to pass the homework. Please, 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 if I put something up on Blackboard, unit 5, 6, 7, whatever it is, 1 through 5, 1 through 7, please read everything, watch the videos, read the articles inside and out from front to back, read the notes section. As a matter of fact, it takes me longer to produce this content than it does to actually do the lectures. It takes hours and hours and hours and hours, and there's a reason I do it. I want to make sure you have enough information. Now, I can cherry pick some of the more important concepts and try to assess you or quiz or test you or homework you on them. But it's only a fraction of what you need to know. What's in there is you have to get the information. You have to get the concepts. And it's impossible for you to get them by just doing the homework. You do have to get all that information, absorb it. And the homeworks are pretty much just to say, hey, are you at least on sort of the right track? If all you're doing is taking the homeworks and finding the answers, you're going to fail, or you're not going to be a success, or you're not going to understand the content. So when we get to ABO testing, NCLE testing, licensing testing, you're not going to do as well. But if you sit down and read everything from start to finish, cover to cover, and understand it, you're going to be that much more prepared. So I am assuming that you guys are going to be adults and college level students, instead of just once a week opening things up and doing the homework. So that's my little stump speech. That's my little, I'll get off my little soapbox here, if you will. And so today what we'll do is again, we have an article, we have a website, which I'm going to walk you through the website today, but you do have to read through the PowerPoints, you do have to watch the lectures, you do have to read these. So what we're going to do is herein, this was a little PowerPoint we put up, and I'm using this as a cross section of a person's eye. And if you can imagine, this is the back surface. It's not to scale, obviously. And this would be my limbus from side view. This would be the cornea. And notice I've made the cornea just a little steeper so it will stand out. And generally, what we're talking about when we're doing if we were doing a soft lens, the soft lens would sort of match this and it wouldn't be in contact, but there'd be a thin layer of tear that would essentially match up, and it's inconsequential. It's only the lens that provides power. But for gas permeable, pretend this yellow thing is a lens. And just like an eyeglass lens, we have a front surface, we have a back surface. And remember, the back surface of the lens, we did the anatomy, and generally, to be more specific, there's the central posterior curve or the base curve, and it can be specified in diopters or in millimeters of radius. If I were to draw out a line, if this were a curve and I continued this yellow circle, the yellow back surface, and went in a specific and continued off to one entire circle, that radius would be the radius of curvature. And it can be steep, it can be flat. Smaller radii are steeper, the longer radius of curvature would be flatter. But in this case, just be aware that the back surface of this lens here, and normally there would be peripheral curves to allow tears to flow in here, and it wouldn't quite be this sharp, but this is for demonstration purposes, just to show you what a tear lens theoretically would look like. Now, if you look at the shape of the front of this eye, the corneal curvature, and remember, we could look at this through topography, we can look at it through our keratometer manual, we can get autokays, but we're trying to, and again, this is spherical in nature. Our corneas tend to be flatter off to the edges, but I'm just trying to get you the idea of how this works and why it does what it does. So if I have this gas permeable lens, it's not really going to match the surface of the eye. It's going to sort of maintain its shape. That ergo, we call it a rigid gas permeable. Rigid lens. It doesn't really flex all that much, so it should keep its shape once we put it on the eye. In this case, I've specifically made this shape of the cornea and the shape of the back of the lens to about mimic one another. And remember, the way that a GP works, and one of the methods is not only does it get oxygen through the lens, but it gets oxygenated tear film every time you blink through a pumping mechanism behind the eye. And there is, in this little white space here, going to fill up with tear film, tear, aqueous, water, for lack of a better word. And just like your cornea has an index of refraction between the aqueous and the cornea, your contact lens has an index of refraction. Well, our tear lens also has an index of refraction. And if you have a front curve, ignore the yellow, ignore the blue, but just this little white strip. Imagine if this were a lens it's got a front curve, which is the same as the back of the contact. It's got a back curve, which is the same as the front of the eye, and it's got a material in it, a refracting material. It's not poly, it's not plastic, it's not glass, but it's a tear. And so that's going to have a refracting power of sorts. Now, in this particular case, if the back surface of this lens and the front surface of the cornea are about the same, which in this case, this diagram, it's going to be plano tear lens. And we would use this mathematically to try to determine it. So if I were to tell you the back surface, the central posterior curve, CPC, or the base curve of the back of the lens, and I were to specify it in diopters and said, hey, this is 43 diopters steep, which remember is approximately the same as the average cornea. And this particular patient was an average patient, and this was also 43. The front of the lens would be 43. The back of the lens would be a 43, so you add the two together. If it's convex, it's positive. If it's concave, it's negative. So it's 43 plus a negative 43, or 43 minus 43, however you want to write it out. And that in turn would give me a lens power of 0, or as we say in optics, it's a plano tear lens. Now here's where it gets interesting. Unlike with soft lenses, whatever the lens power is, that's what they get. Well, in contacts, gas perms, you have to take into account not only the power of the lens that you put on there, but the power of the tear lens. So the tear lens plus the contact lens will determine what power reaches the eye. In this case, it's a non-issue. We've made the same curve for the front of the tear lens and the back of the tear lens, so it's a plano, so it's a moot issue. It's inconsequential, but that's not always the case. And here's a new concept, and that is, let's look at this contact lens. Again, there's no peripheral curves, but just to draw it out, the yellow is the contact, the blue is the cross-section of the cornea, the eye, and notice how the steepness of the contact lens versus the steepness of the cornea, Well, in this case, the back of the gas permeable is going to be steeper then. So this lens would be steeper than the cornea. Well, if this white area fills up with tear film, you're going to have a tear lens that is thicker in the middle and thinner on the edge. Well, that looks just like this white area looks like a plus converging lens. It'll be thicker in the middle, thinner on the edge. And so in this case, same thing. Let's just say the same patient was a 43 corneal curvature, but this time, exaggerated for you to see it, but this would be 44. Well, 44 diopters is steeper than 43 diopters. And so if we did the 44 minus 43, or 44 plus a negative 43, this would give me a tear lens that is a plus 1 diopter in power. Regardless of what I put in the yellow, this could be plus 1, minus 10, plus 40, well, not that high, but in most cases, but this could be any power in the world that I want it to be. And it's one power, it's a spherical lens. It's either minus 1, plus 2, makes no difference. In addition to whatever I put on this lens, there's going to be this tear lens that I've produced by fitting it in such a manner that it's a little bit steeper than the cornea. Well, what happens if I did the opposite? Here, notice how the back surface of this gas permeable, this curvature, notice how it looks a little bit less steep than the corneal curvature. Well, if you look at this, if I were to draw in the edges of this here, look at where the white is. It looks a lot like a regular minus or diverging lens. So if in this case, same person, the keratometry readings are a minus 43, it's a 43 diopter, but the back surface of this tear lens would be a minus 43. Let's say we fit this contact lens at a 42. Well, 43 minus 42 minus 43, you got to keep your signs correct. This would give me a minus 1 lens. And again, this is where it's important. This lens adds with the tear lens, and you put the two powers together, and that's what the patient actually looks through. Not just the contact, not just the tear lens, but both. So in this particular patient, I could have fit a lens that was on K, or the same curvature as the cornea. I could have fit it steeper than K, or steeper than the corneal curvature, the flattest corneal curvature, or I could have fit it flatter than K. And in all cases, I would have to adjust the power of the lens each and every time in order to get the right prescription to the patient. And they'll all see better, but I'll have 3 different lenses that are 3 different curvatures on the back. They'll actually have to have different powers in the contact lens to get my patient the right script. And we'll get to that in just a moment. But the biggest thing is, depending on how I fit it, if I fit it the same curvature, it's plano. If the back surface of the contact lens is steeper, it's going to result in a plus tear lens. And if I fit the contact lens So they needed a -3. But if you'll notice, by fitting this lens flatter than K by half a diopter, um, regardless of the lens we put in there, we've already added to the system a -0.5 diopter by fitting the lens flatter than K. So the contact lens prescription can no longer be a -3 because we already have a -0.5 there. Not in the contact lens, but in the tear lens that we've created by putting this shape of a contact lens on there. So same thing, we'll use the same example. It's a -3 with a 42 diopter. Um, again, there's a typo, so let me just fix this. It's a different example that I was writing. So assuming here that the doctor wrote a -3, we measured it at 43, we put a gas permeable that was a half flatter than K. By making it a half flatter than K, the tear lens is already a -0.5. It's there with the tear lens, but the patient needs a -3 total. What we need to look at is what power should we put in that rigid gas permeable lens in addition to the -0.5 to get the -3 they need. Well, in this case, you have to add both the contact lens and the tear lens, and we want it to result in the power that we want to give to the patient, which in this case is a -3. So in this case, let's order a -250, because if the contact lens on the eye was a -250 and the tear lens was a -0.5 because we fitted a half flatter, we're going to get the -3, which is what the doctor prescribed in the first place. It sounds counterintuitive. You just said, Doc, they need a -3. And you gave them -250. No, that's immaterial. It's you asked, they need a -3, and you gave them a total of -3 between the regular contact and the tear lens. It came up to be -3, and that's because we created a tear lens of a -0.5. We had the contact lens that we ordered at a -250, and you add the two together, -2.5 and a -0.5 gives me a -3, and that's exactly what this patient needs to see well. So if you think about it, it's important for the gas permeable, unlike soft lenses, you need to take into account the tear lens that we created when we figure out what the power of the gas permeable lens is. The term we use is the Beck vertex power. That's what you read in the lensometer. That's the strength of refracting power of our contact lens, or our eyeglasses for that matter in most cases. Since there is no tear lens in a soft lens, and they match a shape, you don't have to factor this in. But for gas perms, because they maintain their shape, like we mentioned earlier, that may, if you fit it the same curvature, the tear lens is plano, you can ignore it. But the second you go flatter than or steeper than the cornea that you're on, you're going to induce a tear lens, and so you've got to make an adjustment. What's that adjustment? Well, this is where we came up with SAMFAP. And in a nutshell, if we fit the gas permeable that's steeper than the patient's cornea, the tear lens is going to be plus. If we fit a gas permeable that's flatter, it's going to result in a minus tear lens. Well, because of that, we have to adjust the prescription to account for, or adjust for, or for lack of a better word, cancel out the plus lens if it goes steeper, or we have to cancel out the minus lens if it's flatter to get the power the doctor wanted. So in either case, we have to adjust the power. If it's a steeper lens that gave us a plus lens, we've got to add minus to the power we're ordering by the same amount the lens is steeper to make sure that the power that the patient gets is what the patient was, what the doctor asked for. If we fit the flatter, which would have given us a minus tier that we didn't essentially need, or we have to factor it in, we're going to add plus. For any lens we fit flatter than the cornea, we'll have to adjust the gas permeable sphere contact lens power by adding plus to the power that we're looking for at the corneal plane. And again, if we went a quarter steeper, a half steeper, 3/4 steeper, whatever the number is, that's the amount that if you fit it flatter, you want to add plus. Well, steeper, add minus, flatter, add plus, or SAM, S-A-M, F-A-P, or SAMFAP. This is something that